All right, welcome back. This is going to be the sixth video here in our S1 equation series. So far, we've discussed 4 of the 5 variables that fall within the equation. And we know that S1 has to be less than or equal to the lowest of refusal speed, maximum braking speed, and rotation speed. However, it must also be greater than or equal to the highest of ground minimum control speed and critical engine failure speed. And that is going to be the topic of this video. So what is critical engine failure speed? Critical engine failure speed is defined as the speed at which one engine can fail, and the same distance is required to either continue to accelerate to liftoff speed or to abort and decelerate to a full stop. So, critical engine failure speed defines a certain distance. That distance is called critical field length. Critical field length is the total length of runway required to accelerate on all engines to critical engine failure speed, experience an engine failure, and then continue to lift off or to stop. It is used during takeoff planning together with the climb-out data to determine maximum gross weight for a safe takeoff and climb-out. For a safe takeoff, the critical field length must be no greater than the runway available. So what does that mean for me and my takeoff planning? Well, let's say we're in our T1 and we're accelerating on 2 good engines to my critical engine failure speed, and I lose an engine at critical engine failure speed. All right. What the definitions say is that it will take me the same amount of runway if I decided to abort to bring the aircraft to a stop, or it will take me the same amount of runway if I decided to continue to accelerate to my rotation speed and take the aircraft airborne. That distance required is called critical field length. So I've accelerated on 2 good engines to critical engine failure speed, and if I decide to abort, the amount of runway required left over for me to stop is called critical field length. In the same sense, if I accelerated on 2 good engines to critical engine failure speed, decide to continue the takeoff, the same amount of runway is going to be required for me to accelerate, to rotate, and take the aircraft airborne. Let's look at this another way, maybe a little bit easier to explain. All right, so on the bottom axis, we have speed and distance. So in the first set of data points, we're going to draw a line of data, and that is going to be named abort. So as our speed increases, it should take us more distance to stop. And let's think about this. So at 0 knots, let's say we lose an engine. We are not moving, but we lose an engine at 0 knots. How much runway will it require for me to stop? Well, stop scratching your head. It's a pretty easy answer. It will take 0 amount of runway, 0 feet. I do not need any runway to stop because I'm not moving and I have no energy at 0 knots. Now let's think about this. Let's say I roll down the runway and I reach 120 knots. There we go, 120. And I lose an engine here, but I decide to stop. How much runway is it going to take for me to stop, to bring the aircraft to a full stop safely? Well, I don't know that data, but it makes sense that if I'm at a higher energy state of 120 knots, it will take a lot of runway required. So as I increase in airspeed, and if I lose an engine at a certain airspeed, the higher that airspeed is, the more runway is going to be required for me to stop. Now vice versa, let's add a second set of points here. Let's change the color so we can kind of see it better. Here. And we'll call these this set of data takeoff. So again, let's start at 0 knots. If I lost an engine at 0 knots, so right here, how much runway is it going to take for me to take off? Well, it would take for me essentially the maximum amount of runway. I don't know that distance, but I know that it's going to be a lot. The runway required for me there is going to be pretty substantial, relatively speaking. But as I increase airspeed, let's say I lose an engine at 120 knots now. How much runway is it going to take for me? Well, let's start here and move up. Oh, there we are. And we move over to the left to determine our distance. And we see that that runway required is pretty small, relatively speaking. Right? We're at a higher energy state. We don't need that much runway after losing an engine here because we're pretty close to taking the aircraft airborne. Now, let's change one more time on the color so we can kind of see it better. What critical engine failure speed states is that if we lose an engine at this critical engine failure speed, it's going to take the same amount of runway for us to abort or continue the takeoff and take the aircraft airborne, right here. And that's where these two graphs meet. And that distance, where they're the same, is called our critical field length. Hopefully that helps you see a little better. So why is this important to me? Let me go back and change again my pen color here. So why is it important for me that S1 is greater than or equal to my critical engine failure speed? Let's say critical engine failure speed's here. Here's my T1. And for instance, let's say that we decide to commit to the takeoff before critical engine failure speed, right? So we're committed to the takeoff at S1, and at some point while we're accelerating to reach critical engine failure speed, we lose an engine here. Where are we going to rotate? Well, we know that first off, if we lost an engine at critical engine failure speed, that critical field length is this long, right? Well, let's say we lose an engine at a lower airspeed, the critical engine failure speed. We have to continue the takeoff. So where are we going to take off at? Well, let me change my color again to kind of help it see it. Boom. Let's say we lose an engine right here after S1, but less than critical engine failure speed. Our distance to rotate is unknown, but it makes sense that we're going to have a greater amount of runway required to accelerate. That's no good, right? I don't want to rotate past the departure end. That's probably an unsafe situation. So in that sense, I want to be committed to the takeoff at or above critical engine failure speed, such that if I were to lose an engine after critical engine failure speed, I know my distance to rotate. I know it's going to be less than critical field length because I've accelerated past my critical engine failure speed. In which case, we've just described our last variable of critical engine failure speed. And in the next videos, we're going to determine how to calculate reference zero and a few ways to that, as well as choosing S1 and why we choose certain variables to determine our go, no-go speed.